Hello, everyone. Welcome to this lab 9 introduction video. In this lab, we will implement a convolutional neural network on the FPGA based on the structure of the systolic array. Okay, so on the FPGA, there are a lot of structure, or there are a lot of design to implement the systolic array, and the structure we're gonna use in this lab is based on this paper. Okay, if you are interested, you can search it in Google and look into the details. We will skip that for this video. And this image shows the structure of this systolic array. You should be familiar with the systolic array already, right, in the previous lab. But for this time, it's a little bit different. Um, let me use the slides for introduction. Let's take a look at this. So PE is still the same as we used in the previous labs. Okay, uh, they are they are connected with each other in this mesh grid. So they have some connection between the neighbors, and also we have some buffers here. So here on the left we have the weight buffers, and on the top we have input buffers and the output buffers. The reason we have the buffers is that we will do a lot of computation here. And to be specific, in this design for the neural network, we will do the classification of the images. So we will have to save those images and the weights as a result of the training. So those are a lot of data, right? They have to be saved into some places on the chip. So for example, we have the data on the DRAM on the chip, and we want to fetch them from the memory and push it into this systolic array. So this is why we need some buffers as an internal place. All right. Okay, we have so the whole module of this systolic array, the interface is like this. We have the input port, we have the output port, and we have the weight port. Yeah, here. So as you can see here, we have the weight in and out. We also have this probe, but this was used for the debugging purpose, so you can just ignore this. Um, Let me see. So in this design, you will need to implement 3 designs, all right? From the top to the bottom, you will have first you will have is a systolic array design, where you just need to create the connections between the buffers to the ports of this module. Yeah, that will be it. And then to go further, you will need to implement this array.v. This is a part. If we eliminate the buffers of this design, you will have a purely PE array, right? This is what we do in this array.v here. We just we have all the instance of the PE ready, and you need to make the connection between them. This is very similar as what you did in lab 8. Okay, and then let's go further down one level, and finally you will also need to implement the PE by yourself. Okay, so the diagram is listed in this figure. Let's introduce the details from bottom to the top. Okay. So the first you want to do is implement this PE.v. So what this PE does, basically there are two functionalities. All right. The first one is to do this multiplication of the input data in and the weight in here. All right. And also we will do a accumulation or say a summation with the multiplication result with this. We have a buffer here to save the previous result here. Okay. So yeah, so this is a buffer, and every time we have this multiplication, we will accumulate it with the previous output here, and you can see the data goes back here, right? And then we can choose to send the value of this buffer to the output port here, right? You may be curious why we have this control here and what this is doing here. This is very similar to your previous design. As you can see in this whole picture, um, so the input of the PE comes from the top, right? And the weight comes from the left. And for the PE inside of this array, the input and the weight actually comes from its neighbor, right? So one of the function of the PE is to populate this input and the PE to their neighbors on the right or on the bottom, right? And for the output, actually, the output of HP is not directly connected to these output buffers, but the output has to be populated through each levels to their neighbors and until the first level of the first row of this PE are connected to the output buffers, right? So this is why the output of this accumulated result can be pushed to the output, or the output comes from its bottom neighbor and then be populated to the top layer, say to the top level. Okay. Of course, we will have this control to decide whether the output is connected to its previous output or its internal buffer here. All right. So for the code here, this is the pe.v you're gonna use. Let's look at the code. So the I and O here denotes if it's an input port or it's an output port, and this is whether gonna be in. This is the data in, or the W is a weight here, or the out means this output from the previous neighbor. Okay. Let me see. Okay, so we have already created some registers for you. As you can see, these 4 registers are actually those boxes in this design. All right, this is one for the buffer accumulating the product, right? It's here, and also the OIN and OW is a register right before the output of this module. And also we have this OUT is here, right? So on the reset, you will need to reset all the registers we have to 0. And then if it's not reset, we will connecting those wires so that the in is populated to its neighbors, the weight is populated to its neighbors, and we will also output the out here based on the control. All right. So we have already created a wire here. For you, you can directly use this. So this is so this line basically means if control is 0, the output is connected to its previous input, this one, all right? So if the control is 1, the output is connected to the buffer. It's this connection. All right. So for here, you will assign the values for each registers here, and also you will be using this. And basically, that will be it for the PE design. All right. If you finish this, we can go one level up and connecting those PE modules into an array, where this is what you need to do in this array.v. All right. Let's look at the interface. So still we have the clock reset and the controls. We have the ins, waits, and the outs. All right. Also, the size are parameterized, so you cannot really hard code the size, but you have to use those parameters for the size. Okay, because there's a possibility that those numbers can be changed from these default values. So we have, let's look at this array. This is a loop unrolling. So we have already created the P array for you. So you can see for each row and column, we have for each row and column, we created PEs, right? And the ports are connected to those wires already created for you. Input, 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 output, output, output for the data in, waits, and out. All right. This is a 2D wires with each of the wires with a width, data width of this size. All right. So yeah, we have already created the P array for you, and what you need to do is connecting the wires between them. All right. Here we are. Also, we have an example here. We will use the same pattern here for each row and each column, and we have an example for connecting the inputs and outputs. All right. So this is basically this is meaning that for the first row, the input of the data in is coming from it's coming from the input ports of this module, this array, right? And for the rest of the rows, the data in input comes from its previous neighbor PE here, right? This is the output port of the data in on the previous rows, right? In the same column. So we have already done the in for you. And you will also need to connect the weights of, so which means those are horizontal arrows, and also the outs. All right, out are these solid arrows here. Yeah, basically that's it. So one thing you need to pay attention is for the last row, the output is 0, right? It's not shown here, but the out in, let me see here. Okay, the out in should be 0, right? Because there's no neighbors on the bottom. So yeah, so you just need to do those connections in this array.b. And after you finish this, we will keep moving forward. And finally, you will have systolic array.b here, where you also connect those buffers together. All right, let's look at this part. Oh, by the way, we still have the controls signal into each PEs here, but these are already connected for you, all right? So you don't have to worry about this control logic. Okay, let's go back to this systolic array. As you can see here, we have instantiate an array. This is the design of this array.v, all right? And also we have created the buffers We also have already implemented the I buffers, input buffers, and the output buffers already. They are written for you, right? If you're interested, you can look into that, but this is not required. And also the weight buffers and the input buffers, they are just in different directions, but they share the same structures here. All right. So for the weight buffer, it will also reuse the design of these input buffers here. So as you can see, we have created those three buffers arrays here for you. So from I equals 0 to I less than number of rows, we use the design of the IB, but here we are creating the weight buffers here. All right, so for this design, for this size, we have created 4 weight buffers, and also here for each columns we created input buffers and output buffers. All right, those are already created for you, and the ports are already connected to those wires created for you. Okay, as you can see here. And what you need to do is connecting the input ports and output ports of this design. These 3 ports, they should be connecting to the buffers, right? To be specific, the weight should be connected to the very first weight buffer. Data in should be connected to the very first input buffer, and the out should be connected to the first output buffers. All right, and by the first, it should be the one with index 0. All right. So what you need to do here, we have already provided an example for you on how to connect the weight buffer here. So let's see. So for the first one, the weight buffer's input comes from W. W is the input port of this design. And then for the rest of the column, the input of the weight buffers comes from its previous neighbor here, from the buffer I minus 1, right? So yeah, so this is just this one column. And also you will do the same for the data in buffers, input buffers here. All right, this should be most likely very similar to this part. All right, and then you will do the connection of the output buffers. It should be the same, but with one exception. That is, for the last column, the previous output of the buffer is 0. This is the same as here, right? So the input into the last row of PE should be 0. And the same here, for the last output buffers, there's no neighbors on the right, right? So the input into this output buffers should be 0, right? So this is for the last column. And yeah, I guess this is all you need to do here. Pretty simple, right? Let me see. Yeah, basically what you need to do is those connecting wires to the correct ports or the entities. And then I will talk something more to help you understand the whole design, right? Yeah, this is a scheduling when we do the convolution here. Very similar to the structure we did in the matrix multiplication, but of course this is more complicated. And this is actually the equation for doing the convolutional operations. All right. This is a proposed CNN here. So the input data is this data set, MNIST. Those are handwritten numbers here. and we need to classify them into either it's 0, 1, 2, 3 until 9. All right, just detecting each of this written image. What are they? What are they? So the input image is a 28 by 28 image, and we will have a neural network with several layers here, all right? And lastly, we will have 10 outputs, all right? Each one corresponding to one number between 0 to 9, right? So we will input one written image, and then we have 10, I would say it's like cost, but you can think of it like a possibility that which number this image belong to, right? And it will take the most likely one and just say, okay, this image is denoting this number, all right? Um, Let me see what else. Oh, we also have the controller design. So, which means we have this systolic array, right? But we have many layers, and we have to decide which data comes in first into this structure. So this is why we have the controller, basically control the whole logic of the whole scheduling of the whole operations, and they are implemented in this part, matrix calculation of E. As you can see, there are many states here. We have the idle states, we have load wait, load input, and calculation, and out, and some loop and reset here, right? This is just like the state machine you have been using many, many times. You can see the load wait, load in. Yeah, those are some complicated logics you don't have to worry about. They are already implemented for you. All right, and we have after all these implemented, we have this very top module. As you can see, we have created the block RAM here. Probably we will just use 2 block RAM here, but I will double check. Or maybe we only need 1. Never mind. Just ignore this part. And we have this matrix calculations, right? We implement it here, and that will be it, right? So after you finish all these, you will do this on the board. Of course, there's no test bench since it's so complicated. You cannot simulate the whole thing. But on the board, you will have to run this CNN test, and we also have the CNN data you will need to copy to the SD card, right? And after running this, it will run some tests and gives you some accuracy when we run the test. Okay. Of course, we have the ground truth so that we can know the accuracy. If everything is all right, you will have an accuracy. If I remember correctly, it should be around 95%. Okay. Um, I guess that would be it. All right. Thank you for watching this video. Good luck. Bye bye.